Okay. All right, everybody, let's get started. We are in lecture 34. I was showing this right before class started, but to put it in perspective, this is my sort of notebook that I use. It has like a lot of calculations for all the examples. And like, this is where we're at in it, you know, so we're there. We're definitely near the end. Okay, so a couple of housekeeping items. So on Friday, we are not meeting, okay? So the way the schedule is going to work is, and let me go back a slide just to make sure that everybody's on the same page. So today, we're covering shear and moment diagrams, part 2. What we're going to do is we're going to finish our discussion there by looking at how the construction of shear and moment diagrams change if we're looking at distributed loads instead of concentrated loads. And then Friday, that's going to be a pre-recorded lecture. I've got 2 lectures that involve friction. One just goes through the concepts, and then the other gets a little bit more into the details on the problems. And really the only thing that makes this one, I don't want to say trickier, is trigonometry, because we start taking objects and we put them on an incline and whatnot. But if you've had Physics 211, I don't think that there's anything in this lecture that's terribly new, because we're just talking about coefficients of static friction, coefficients of kinetic friction, normal forces, probably stuff that you've seen in Physics 211. If you haven't had Physics 211, I take it pretty slow. The idea is that it's not, this video isn't too heavy on the math side of things, and it'll get everybody up to speed. I'll have that posted on the playlist, bless you, probably either sometime today or tomorrow. Okay, Monday we review for the exam. Wednesday we celebrate. Friday class is canceled, so you all get 2 Fridays off. Is that okay? Now you have to make up your this lecture or whatnot by watching that video, but you can watch that sort of on your own time. Okay, so just to make sure it's clear on the assignment schedule. So today homework 6.3 was due. How was that? Hopefully that was pretty simple. Was that pretty straightforward? Anybody have any questions on it? Okay. Homework 6.4, I'm going to assign today, and it's going to be due Friday, and then you are not going to have another homework assignment until the Wednesday of Dead Week, okay? And it's not long by any stretch of the imagination. It's not like, oh, I'm going to give you all this time because the homework's huge. It's not. The only reason I'm waiting until after, to the Wednesday of Dead Week, or sorry, pre-finals week, is that this homework covers friction. And so we're going to cover it a little bit in this video and then a little bit in this lecture. And I didn't want to have a homework due the Monday when you come back, so I figured I'll give you till Wednesday. Okay, does that make sense? Because at some point, I don't want to be one of those professors that says, enjoy your break, here's this amount of work that's due on Monday. Because I never really liked that. So, but I do want to have one sort of exercise with friction, because friction will be on the final. Okay, so yeah. So in terms of homework, you've got a homework due Friday, and then that's it until after Thanksgiving break. Sound good? All right, let's get into structural analysis, shear and moment diagrams for distributed loads, okay? And I want to be clear that the theory and the ideas don't change from the last lecture. And what I mean by that is when you go through and derive your relationship between loads, shears, and moments, we weren't really looking at a particular load case. We weren't looking at, whether it was distributed loads or triangular loads or anything like that. We were just looking at a being subjected to arbitrary loads, and this is what we got. Now, granted, I'll say that if we were to get into the weeds a little bit, if we were to look at it using, let's say, point loads, the math might have changed a little bit, but in the end, the same relationship would have been arrived at. The idea that if I have the loads and I integrate those loads, I get the shear diagram. And if I integrate the shear diagram, I get the moment diagram. And then we develop these conclusions. I would argue these conclusions are going to be really, really important today. Okay? And so, like, for example, if you've got your load diagram or the free body diagram for the structure and you want to draw the shear diagram first, you do need to recognize that the slope of the shear diagram at any given point is equal to whatever the load is. Okay. Now, on the last homework and the last example that we did, we just had a beam with a series of point loads on it. So really, the shear diagram just looked like a stair step, had these series of horizontal lines. Because between those point loads, there was no load on the beam. So there was no slope on the shear diagram. The shear diagram slope was 0. Okay, so that's why it kind of looked like a stair step. The shear diagram isn't going to look like that today when we start looking at distributed loads. Now, between 2 points, if I want to determine the change in shear, it just is equal to whatever the magnitude of load is between those 2 points. And again, that just comes from our conclusions here. Similarly, on the shear and moment diagram, the slope of the moment diagram is going to equal whatever the shear is. And that's going to be interesting because the shear diagram values are going to change, so the slope is going to change. And so that's going to change what our moment diagram looks like. But we are still going to be able to use the idea that we just integrate the shear diagram to get the moment. Now, I got to make a point right now, because this is really important, okay? And so I want everybody to pay attention to this, okay? Let's take a look at this image here on the screen, okay? So we've done support reactions for structures with distributed loads before. We've done that before, right? And so what we would do is we'd say, okay, here's the beam and I've got this distributed load. What I'm going to do is I'm going to take that distributed load and I'm going to collapse it or idealize it as a single concentrated force. The magnitude of that force is going to equal the area of the load, if you will, that area. And then I'm going to place that load wherever the centroid is, right? We've done that already in here. So far, so good? Now, here's the thing, okay? That is totally fine for computing the support reactions. But when you go to construct the shear and moment diagrams, this is incredibly important. You need to revert back to the original loading on the structure, okay? That is a very common mistake that students will make when they're first starting to construct the shear and moment diagrams. Let me explain why, okay? So here's this table, okay? Here's this table, all right? Now, let's say, for the sake of discussion, that I put 200 pounds on this table, okay? And let's say that I place it symmetrically. Now, if I place 200 pounds on this table and I place it symmetrically, how much is each leg going to experience? What's that? 100, right? I put 200 pounds symmetrically on the structure. I get 100 pounds in each leg. That's simple, right? But now instead of focusing on the legs, I want you to focus on the table. Specifically this wood plank right here. What do you think is a worse scenario? Taking that 200 pounds, lumping it right in the middle, or instead taking that 200 pounds and spreading it out over the length of the beam? Which is worse, lumping it in the middle or spreading it out? For the table. Lumping it in the middle, okay? What I'm saying is that whether you lump it in the middle, okay, or spread it out, it doesn't change what the table legs are seeing, but does change what the table face is seeing, what the surface of the table is seeing. Does that make sense? So it's okay to collapse this into a concentrated force when you're computing reactions. But when you go back to constructing the shear and moment diagrams, you've got to go back to what the load originally was, or your shear and moment diagrams are going to be inaccurate representations of what's really going on the beam. Does that make sense? Okay, I just really want to make sure that that point was pretty salient. Okay, now let's take a look at what happens when you look at distributed loads and you start constructing shear and moment diagrams. You go back to those derivative integral relationships that we mentioned earlier when we start looking at polynomials. Okay, the load in this case is a constant. Okay, so let's just go back to Calc 1. Okay, if I have a function y equals 6, okay, so that's a constant function, y equals 6. I take y equals 6 and I integrate it. What do I get? What is the integral of 6? It is 6x plus c, right? Okay, so if I integrate a constant, I get a line, okay? So the integration of a constant load will yield a linear shear diagram, okay? Now I've got this shear diagram constructed in a very specific way. Here, the load is going down, okay? So if the load is going down, instead of y equals 6, we're really talking about y equals minus 6. The constant is negative. And so if I integrate a negative number, like negative 6, I get negative 6x plus c. this line, the graph of this line, is a line with a negative slope. It's going downward, okay? So that shear diagram represents the integral function of the load diagram, okay? But now let's take it one step further, okay? So let's say I have a line. We'll call it negative 6x plus c. What is the integral of that? What if I integrate it one more time? The integral of negative 6x plus c, well, it's going to be negative 3x squared plus cx plus a new constant d. It's going to be a parabola, right? So if I take a linear function and I integrate it, I take that linear function and integrate it, I get a parabola, okay? So when you deal with distributed loads, you get linear shear diagrams and you get quadratic moment diagrams. Now the way these are constructed is again, goes off that integral relationship. So take a look at the shear diagram. In this region, we're going from a high shear region to a low shear region. So if we're going from a high shear region to a low shear region, we're going from a high slope region to a low slope region. And what does a parabola look like if it goes from high slope to low slope? It opens downward like you see right here. What is the change in moment from here to here? How much do we jump? To whatever that area is, okay? Does that make sense? Everybody okay with that? All right. Now, I've got an example that we're going to do here in a second. This is going to be the example that we're going to spend the vast majority of lecture on. But before we do, I've got some geometry I want to look at. One of the things I found is that when I teach this topic is that what I just said about linear shear diagrams and quadratic moment diagrams, those ideas aren't that hard to wrap your head around. But then you actually start getting to the construction of your shear and moment diagrams, and you have these geometry problems that you need to solve, and it's like, wait, it's been a while since I've done a lot of stuff like this. So I kind of want to take a step off to the side and just look at the geometry, okay? Because I guarantee you we're going to have a problem that looks like this very soon, okay? So let's take a look at this sort of geometry problem, okay? Now I have, let's say, this segment of a shear diagram that looks like this, okay? And we have a shear diagram that jumps from 25 kips down to, let's say, negative 75 kips, okay? And what I need to do is I need to determine the area of this triangle and the area of this triangle, okay? I'm going to show you a really basic way to do that, okay? Now, the first thing I'm going to do is I'm going to determine the slope of this line, okay? And the way I'm going to do that is I'm going to say, all right, how do we determine the slope of this line? Well, it's the change in y over the change in x, okay? So the change in x is going to be 25 feet. So from here to here, we go to 25 feet. And what about our change in y? How much do we change in y from here to here? Say it again? 100. Now I'm going to go, for the sake of discussion, and for the folks that are cognizant of their signs, I'm going to call it minus 100. Okay, and I'm going to get minus 100. But I'm being very cognizant of my units here. Notice that the numerator has kips and the denominator has feet. So if I divide that out, I get negative 4 kips per foot. That's the slope, okay? But look at what this is. The slope is negative 4 kips per foot. 4 kips per foot, that should be a familiar way of expressing something. I propose to you that wherever this is on this beam, that the slope is 4 kips per foot because that's what the load is on the beam beam in question. That in that range, it's experiencing a downward 4 kip per foot distributed load. So in real problems, you really don't even need to do that calculation. You can just look at the loads and see what they are, okay? Now, in order to determine the areas of these triangles, okay, what I'm going to need to do is determine this distance here. We'll call it B1. Actually, let me leave that part out. Let's do that. B1. And then this distance right here, B2. Now, I would argue again that slope is rise over run. Okay? So if slope is rise over run, then the run is the change in y over the slope. And if that's the case, and B1 is just (25/4). And 25/4, I think, is 6.25 feet. B2. Let's see if I can do that one in my head. 37.5, 18.75. So I propose that this is 6.25 feet. This is 18.75 feet. And do those pass the smell test? Do those make sense? Well, if I take that and add that, what do I get? I get 25 feet. Okay? So then, how do I determine the area? Call that A1, A2. How do I determine those areas? Well, A1 is B1, H1/2, just the area of a triangle. So 6.25 feet. I might need some help on this one. 25 kips over 2. What is that? I might need somebody to break out their Casio FX115 ES Plus or similar scientific calculator. We'll say 2 decimal places. While you all are breaking out the calculators, we can set up the other one. That one's going to be, we'll call that one negative since it's going to be a negative area. What do we get for the first one? 78.13. And notice the units are going to be foot kips, which, I mean, that's a moment. We're integrating a shear diagram, so we should get a moment. What about the next one?
Negative 703.13.
Say it again.
Negative 703.13.
Negative 703.13. Do I have seconds on both of these? Okay. Does that make sense? This is really basic geometry, but I don't want this to get in the way of what we are about to do. The real deal is the example we're about to do here in a second. Okay? But I'm going to stop for a little bit and see if this makes sense. Anybody have any questions? Okay. Do you mean leave it here for a second, or are you good to go ahead and move on? Okay. All right, did I copy it? Good. Okay. All right. So let me drag this down here just to get it out of the way. Okay. So what we're going to do is we're going to draw the shear and moment diagrams for this this structure. Okay. This one's obviously a little bit more involved than the last one. I decided to ramp it up a little bit because not only do we have concentrated loads, but now we've got this distributed load that we need to deal with. Okay. We have 3 kips per foot over a total distance of 60 feet. We've got a hinge support and a roller support. So we need to go ahead and handle each of these. First, by determining the support reactions. Now, remind me, we have a pin supported A, so how many potential reactions do we have there? 2, right? So we'll call that AY, CY, call this AX. But do we know what AX is going to be? 0, yeah. For a lot of these beam problems, that's going to be the case. Okay? Now, okay. Now, before we start going through the effort of computing support reactions, let's deal with the quirky part of this problem right now, which is that distributed load. Okay. Now let's use a little bit of common sense. Okay. So I have 3 kips per foot, and that is applied over a total length from A to C. So that is 60 feet. So how much total load does that represent if I got 3 kips per foot over a distance of 60 feet? Say it again. 180 kips, right? I have 3 kips per foot every 60 feet, so 3, 6, 9, all the way over, and then we have 180. Okay? Now, if I were to idealize that 180 kips in a single spot, how far from A would I place it? Say it again. Just 100% right, 30. Okay? So what I'm going to do, and the way I'll do this is I'll say, you know, let's go ahead and about right here place sort of a dashed line load right there, and let's put 180 kips, okay? And let's go ahead and define that as 30 feet, okay? And so now I think I'm ready to go ahead and start computing support reactions. And just because we have a distributed load or we've got this beam that's overhanging over here doesn't mean we handle it any differently than we've done any other problem, okay? We're still going to sum moments. Let's say we sum moments at A. We still handle this like we have every other problem so far, okay? So if I sum moments at A, I don't need to consider AX or AY. Okay, I have 180 kips times a moment arm of 30 feet. Okay, I'm going to treat that as negative. Okay, the 30 kips, that's also going to be negative. What's the moment arm for that 30 kips? There we go. Let's go ahead and handle that 60 kips. Now, what's that moment arm going to be? From A. $80. There we go. And we'll add to that the moment contribution from CY, which is at a moment arm 60 feet. And so now this should be pretty simple. I think a lot of this I might be able to do in my head. This is 5,400, 1,200, 4,800. All right. And that's going to be plus CY times 60 is 0. And so that's going to be CY times 60 minus, so we've got, let's see, 4,800 and 1,200, that's 6,000. 6,000, and that is 11,400. Therefore, CY is, I don't think I can do that one in my head. What's 11,400 divided by 60? I know it's going to be positive. I know that. 190. Do I have a second? Okay. So there's that reaction. Okay. And, oh, I went too far. There we go. That's good. Make that big. Get a little bit more room. There we go. So by now, this part, I would hope by now should start to get to be pretty easy, right? Because we're just doing what we've done for multiple problems at this point. AY and CY are going up. We have 180 kips, 30 kips, 60 kips going down. We know that CY is 190. All right, so let's see. 190 and 180, okay, that's 10 minus 30 minus 20, and so that's minus 80. So AY minus 80 is 0. So I have 80 kips going upward. I guess to be consistent, let's go ahead and circle that one too. And so those are our support reactions, okay? I did that part a little fast, but is there anything I need to go back on? Anything that was confusing about that? I hope by now that's simple, right? So far, so good? Okay. Now, here's the important part, okay? So now what we're going to do is we're going to construct a shear and moment diagram. I kind of cheated a little bit because I didn't want to have to scroll up and down, so I sort of copied the beam over. Let me make it a little bigger so we can all kind of see what's going on. I'm also going to go ahead and put down, now that I know that this reaction is 80 kips, and this reaction is 190 kips. But notice that I don't want to do this, okay? I don't want to say, oh, I've got to put that there. No, absolutely not, okay? Because what we are about to do here in a second is we are about to plot the change in shear and the change in moment across the span. What's actually going on is there's a force that's distributed over 60 feet. It is not lumped right there in the middle, okay? So again, that lumping of that load in the middle was only so that we could make the computation of our support reactions a little easier for us. But once we get to plotting the shear and moment diagrams, we go back to the beam as is, okay? So this is the beam as is, all right? So now what I'm going to do is I'm going to set up some guidelines to make my life a little easier when I'm plotting this shear and moment diagram. So let's see, we're going to do like we did before. I'll draw some dashed lines, sort of go like this. Do one here. Do one here. And do one here. Okay. Hopefully those are pretty visible. All right. And what we're going to do is we're going to strike a line right here. Okay. And we're going to say that this is the shear diagram. And I'm going to put some little tick marks there just to make sure that everybody can kind of see that's the 0 line. All right. Now, a lot of people are still catching up because I kind of cheated. I kind of just said, ooh, I get to just hit copy and paste and redraw the beam again. So I know that some of you all are drawing some stuff out, so I'll give you a sec to catch up. Okay. Everybody good? Okay. All right. So we handle this again the exact same way that we do for concentrated loads. I start here at 0, and I better end at 0. So I know we haven't handled distributed loads yet, but what's the very first thing I should do right here? What is the beam telling me to do on my shear diagram right here? Jump up 80. So I need to jump up 80 to about right here. That's the very first thing I need to do. Okay? Now, I like to handle this one segment at a time. So let's just go from A to B. Okay? So somebody help me out. How much load is present from here to here? How much load is that? Negative 120. All right? So, if I'm at 80 and I go down 120, where should I be right here? Negative 40. Okay? Now here's where the new stuff comes in. This is a constant load of -3, so my integral of that is a line. Okay? So I'm going to shoot down about like that. I'm going to hit -40. Now, what happens right at B? What happens right at B? I have a negative 30 tip. So if I'm at 40 and I drop another 30, I'm going down to -70. Now, how much load is this? How much load is that right there? From B to C. Well, it's 20 foot long, and that's 3 kips per foot. 60, right? So -60. So if I'm at 70 and I drop down linearly another 60, negative 130. Now what happens? Ooh, big jump up, right? So if I'm at negative 30 and I jump up 190, what's that put me at? What's that? 30 or is it 60? So I'm at negative 130, I jump up 190. Puts me at 60. All right. All right, what happens in this region? How much load is between that region? Nothing, right? No load means no change in shear. I'm at 60. Drop back down to 0. Start at 0 and end at 0. That is your shear diagram. Let me stop for a second, see if this makes sense. Does anybody have any questions on this? All right. What's that?
The initial 80, do we need to account for that 3 kip at the very beginning as well?
No. Because here, that's not a single point load. That's an entire distribution, right? So along that little bit, it would be 3 kips per foot over a width of like nothing. I get what you're saying, yeah. But don't treat each one of those arrows as like an individual point load. Because if that's the case, it wouldn't be a smooth line. It would be, you know. Does that make sense?
Yeah.
All right, everybody else okay with that? If you got questions, please. This is good stuff. Are we good? All right, so now we need to construct the moment diagram. And in order to construct the moment diagram, we need to integrate this shear diagram, okay? So first off, let me scroll like that so we can kind of see the dimensions a little bit. Let's start off with this rectangular region here off the right. So I have 60 kips high, 20 feet long. So 60 times 20 is plus 1,200. Right? That should be easy. Okay. Now, I'm going to show you a little trick for this region right here because there's two ways to handle it. You could split it up into a triangle and get the rectangle and the triangle area separately, or you could do this. Okay. So we have, this is minus 70. This is minus 130, and it is 20 foot long. So if you want that area, just take 20 feet times the average of these two numbers. Because what you're doing is, that's the area of a trapezoid. Essentially, what you're doing is you're sort of splitting the difference, and you're saying, I'm going to cut this triangle off, and I'm going to stack it right there and get that area. That's just the area of a trapezoid. So the average of 70 and a 30, the average of 70 and 130 is 100. 100 times 20, that's going to be minus 2,000. Does that make sense? Again, if you don't want to do that, that's fine. You can split that up into a triangle, a rectangle and triangle, and you'll get that the rectangle has an area of 1,400 and the triangle has an area of 600. Like, I mean, either one's fine. So far, so good? Now, we need to get the areas of these triangles, but by golly gosh gee, we just did a problem like that. So what we need is a length of this and a length of this. Now, before we do that, what is the slope of that line? And you don't need to do any math to figure it out. 3. We'll say negative, but yeah. It's 3 because that's what the load was. It's negative 3 kips per foot. Okay? So if I want B1, I just need to do 80 over 3. What is 80 over 3? What is that? 26.67, something like that? So this is and so that makes this 13.33 feet. So we should be able to get the area of these triangles pretty easily. Let's start off with this one. What is 1/2 of 80 times that? We'll say like 1 decimal place just to keep everything simple. 1,066.8. I got 0.7, 0.7, 0.8, doesn't matter. That's probably close enough. One thing I'll tell you with shear and moment diagrams, I'll just go ahead and tell you now, depending upon your rounding, they're supposed to start at 0 and end at 0. If they start at 0 and end at like 0.1, that doesn't matter. Don't worry about it. That's fine. Now, what about this one? What is 1/2 of 40 times 13.33? Probably something negative. Bless you. I'm getting like 266.7. Did everybody else get that? All right. we sum these up? What's that plus that plus that plus that? 0. That means we're doing something right. Okay. Now I'm going to stop for a sec before we move on. I want to see if this made sense. Does anybody have any questions on this? Very good? Okay, all right. Now, watch this. Okay, so I'm going to continue this down. All right, and I'm going to construct another horizontal line here. Put my little tick marks on here. Again, probably not necessary for what I'm doing on the screen since I'm using colors, but if you're just using a pencil, I find it's a pretty good idea to just make sure you know where the 0 line is. Now, I want everybody to watch up here. I'm going to do something also a little different or add to something, and you're going to see why. I'm going to add another guideline that goes right here, okay, where that shear diagram becomes 0. Just going to add another one from there. And you're going to see why here in a second. Okay. But basically, yeah, the same guidelines as before, right? Same guidelines as before, but I added something there. I added a new guideline right there. We'll extend these downward a little bit. So they're all kind of lined up. Okay. I'll give everybody a sec to get caught up, and then I want everybody to watch as we construct this thing. Okay, all right, eyes up here. Before we start drawing any curves, let's see if we can track our values. Okay, we're going to start at 0 and hopefully end at 0. Okay, so before we start drawing anything, what can you tell me from here to here? From here to here, how much do I increase? What do I look at now? I don't look at the values on the shear diagram, I look at the areas on the shear diagram, right? Because we're integrating the shear diagram to determine our moments, right? So from here to here, I go up that much right there, okay? So right here should be something like 1066.7, okay? I'm not drawing it yet. Right now, I'm just looking at what the values should be, okay? So if this is 1066.67, what should the value be right here? I want to see if everybody's paying attention. Say it again. That's exactly right, because if I'm at 1066.67 and I drop down to 66.67, I'm at 800. 100% right. Okay. Now, if I'm at 800 here, what should I be right here? If I'm at 800, what does this tell me? Where should I be right here? Okay, 1200. So I'm actually going to need to scroll down a little bit for that. That's going to need to be like something like that. So maybe I need to extend my guidelines a little bit. And so if I'm at negative 1200, and this tells me to go up 1200, I'm going to be back at 0. All right, so we at least know that part is correct. Now, this is important. Let me know when you all are ready, because I want eyes up here for this. So watch this. Watch this. Okay, this is the shear diagram. This is the moment diagram. What the shear diagram will tell us is the slope of the moment diagram. So help me out. Right here, the value on the shear diagram, right here, the value is 80, right? Okay, so algebra tells me that if I graph a line right here with a slope of 80, it looks like this, right? Now, what's happening to the shear diagram from here to here? All right, the shear diagram is getting smaller, right? We're going 80, 70, 60, right here where the shear diagram is 0. So what's happening to the moment diagram is the slopes have got to decrease until we get to 1066.67 and the slope is 0. Does that make sense? So what does the moment diagram look like? It looks like that. And in fact, that parabola continues like that. I've kind of got that drawn poorly. Let me see if I can do that better. And I'm going to erase this and redraw that point. I like that better. Sometimes what I will do is I will use the terms lot to a little. What I mean by lot to a little is the shear diagram goes from a lot to a little. So the slope of the moment diagram goes from a lot to a little. Okay? So in other words, it either looks like that or it looks like that. But that second one's wrong because of how the shear diagram is structured. Does that make sense? Okay. So if that's the case, help me out with this region right here. Okay. This region right here. Okay. So we've got 800 and we've got negative 1200. Okay. We've got option 1 that goes like this, and we've got option 2 that looks like that. Which is it? Option 1 or option 2? 1. It's 100% right, okay? Because the slope is going to go from negative 70 to minus 130. It's got to go even more pronounced. All right? So the slope has to sort of take an even sharper turn, go like that. Now, finally, what does the moment diagram look like in this last region? It's a straight line. A constant shear diagram means a linear moment diagram. It goes like that. That, ladies and gentlemen, that is your moment diagram. And so from this diagram, we have a, let's say, maximum absolute bending moment of, well, negative 1,200 foot kips. Like the maximum positive bending moment is 1066, the maximum negative is negative 1,200. So probably if I was a designer, assuming it's going to behave the same way either way, I'd probably be worried about that moment the most. Just as with shear, the worst shear I'd be worried about is that one right there, because that's the highest magnitude on the shear diagram. Does that make sense? I gave you a practice problem on homework 6-4. And remember, homework 6-4 is due Friday. That's the last homework before exam 3. This is the last topic before exam 3. So one final thing. On Monday, we have exam 3 review. Come prepared with questions. All right? That's all I got. I'm going to pull the QR code up again, but that's all I got. I will see you all on Monday.